Okay, well, now we are continuing today on the highway horizontal alignment. And last lecture, we explained or discussed the different types of horizontal curves. And we mentioned that the horizontal alignment is basically, horizontal alignment consists of tangents connected together with horizontal curves. And as we mentioned, we have different types of curves. We have the simple curve, we have the compound curve and reverse curve, and the spiral curves. Then we discussed the main characteristics or the main elements in a horizontal curve, just for a simple curve. And these are the most common curves that you are going to be using. And also we discussed the degree of curvature. Then we derived this formula for the balancing uh, of, uh, of a vehicle on a horizontal curve. And these are basically the design formula for a horizontal curve. So basically, as we mentioned, in order to balance the vehicle, we have to balance it using two elements: the friction on the tire, okay, and the slope on the pavement, okay. So basically, the vehicle, if the road is straight, it drives, straight. So during at a curve, we bank the road like this, similar to aircrafts. Aircrafts during flight, when they turn, okay, they bank. If we look at an aircraft, so during flight, that's the tube of the aircraft, that's the wings, and that's the fin. That's during cruise flight. There's no issue. When it turns, it bank like this. But there is a fundamental difference. What's that fundamental difference? The resistance for this aircraft from sliding this way or sliding the other way is basically done by the banking, by the slope that it takes, or this banking angle. However, for vehicles, the equilibrium of the vehicle is done by two things: by the banking and by the friction. So the centrifugal force that is pushing the vehicle out of the curve is balanced by these two elements. Okay? So basically, while we are designing the horizontal curve, there is a maximum banking angle. Okay? And it says that the ASHTO range from 4 to 12. And for practicality, 8%, that's kind of 12% is very difficult to achieve. Why? I will explain later. 8%, that's the maximum practically. Okay? 5%, that's the typical super elevation that we use. So, and also we have the side friction. The side friction here is function of the speed, as we explained in this horizon in this curve. So that's the speed. As the speed goes up, you see that the side friction goes down here. So let's go back and see why it's difficult to have high banking angle like this. During the construction of pavement, we have to establish this. Okay, we have these banking. We start with the aggregate to make this super elevation. That's the first part. But when we start putting the pavement come from the batch plant in a almost in a liquid state. So here, that's the pavement. When we try to compact it, the equipment, there is no firm thing for the equipment to drive over. Okay, so usually we build a support here. Then we have the finisher. That's the machine that we use to place the asphalt over this part, but supported here, so it doesn't slide this way. Okay, that's why it's difficult to have more than 12% super elevation. Okay, so in designing the horizontal curve, okay, the methodology for the design is based on the maximum consideration for selecting side friction, maximum force drive, passengers and drivers will be exposed on the horizontal curve. So as I mentioned before, we have component from the super elevation, okay, and there is another component by the friction. So basically the force that experienced by passengers on the horizontal curve should be less than the maximum, we try to use the maximum available side friction, but we have to maintain that these forces should not exceed certain value. Okay, if we look at this piece of equipment, this is usually found on aircrafts, okay, and this is for the turn coordinator. And in this situation, while the aircraft is turning, this pole, this is a metal pole, as you can see, this is a metal pole, and this is an arc curve like this. It can go either way. So if the aircraft turn, bank left or right, this pole can go either way. But if it's a coordinated turn, it's going to stay in the middle. That's why while you are on aircraft and it's turning and you are holding a cup of water, there is no water going to spill out of it. And the surface of the water is just plain, it's not affected by the banking angle because the aircraft at that time is turning. The banking angle is accurate, and it's a balanced turn. Okay, here when the ball goes up like this, that means the banking angle is insufficient and the aircraft is shooting this direction. Here the banking angle is too much and the aircraft is shooting, downwards, is slipping. So how does this connect to our ground transportation? We have the similar tool, okay, which is the ball bank indicator. It's similar to the one that we seen earlier in the aircraft. However, this ball is allowed to go from 10 to 10. That means when you are driving the vehicle at the design speed on the curve, this pole should not exceed these values. What are these values? These values contribute to 0.1 G. So what we are saying that we should not we should not expose passengers to more than 0.1 G. Otherwise, they start feeling uncomfortable in the turn. And also, we might, expose the vehicle to overturn, especially if it's an SUV vehicle. If it's an SUV vehicle, okay, sports utility vehicle. سيارات الدفع الرباعي يا شباب. Okay, its CG is high. So if we exceed 0.1 G, we are exposing these vehicles to an overturn. Okay, clear? So we need to maintain at a maximum exposure or a maximum use for F lateral should not be greater than 0.1. Any questions? Okay, now the design methods for horizontal curves. The design methodology, basically, we look for the radius, the E, and the F. The method 1, super elevation, okay, E, side friction, F, are inversely proportional, okay, to curve radius. So the higher the E and the higher the F, the lower the R, okay, in a straight line relationship. Method 2, all lateral acceleration is sustained by side friction. So sometimes we use method 2 when we don't have the flexibility of having super elevation, if no super elevation, or it's not recommended. In method 3, so here they try to use the maximum value for the side friction, then the remaining we start on the E, on the or the super elevation. For the method 3, for road users comfort, okay, we consume the maximum super elevation. So here we use the E max, then we turn to the side friction to to balance the turn. For method 4 is the same like method 3, okay, but using running speed instead of design speed. Method 5, same as method 1, but it assumes nonlinear relationship of E and T. In reality, in most cases, okay, we try to go with method 3 or method 2, depending on the situation. Any questions so far? Let's have an example. Here, for a highway with a design speed 90 kilometers per hour, if the maximum super elevation was set to be 8%, design a horizontal curve and determine the safe turning radius such that the maximum centrifugal force exerted on the passengers is maintained below 0.1 G. What does this mean? Let's solve it. First of all, the design speed V equal 90 kilometers per hour. Okay, so for 90 kilometers per hour, and we have the design formula V square over GR equal E plus F lateral, and we are looking for R. So R, that's the minimum radius, R equal V square over G E plus F lateral. Okay.
دكتور
Yes.
الإي مو كان في قبلها رقم 0.01
It's 0.01.
امم
So I'm gonna put it here as a fraction, not as a percentage. Here you put it
اوكي
E%. When I put it this
اوكي
way, that means E.08. But if I use this one, I put here 8. It's the same. Here you put it as a fraction, not 8%. But if okay, here, correct?
يس
Okay. So let's look for the 90 kilometers per hour. 90 kilometers per hour, it allows for how much side friction? That's the 90 kilometers per hour. It allows for, I think, 0.13. But it says here that the maximum centrifugal force exerted on passengers maintained below 0.1 G. That means F, okay, should be less than or equal 0.1. This is what it means. So R equal 90 kilometers per hour divided by 9.81 meter per second square multiplied by 0.08 plus 0.1. Okay,
Doctor, we have the 90 squared.
the 90 squared. Thank you. What else?
دكتور ال 90 لازم نحولها لمتر بير سكند.
That's good. Excellent. So we have to divide this by 3.6 in order to have consistency in our units. So this is the correct
دكتور
way to do it. Yes.
0.1 مفروض مضروبة في الجي، فبتكون 0.1
Here.
times 9.8.
It's already multiplied. You see it?
Yes.
Okay. That's why I said that F should be less than, because after all, it's going to be multiplied here with G. You get that? Okay, let's solve it. So we have 90. So this is basically 25 square divided by 9.81 multiplied with 0.18 equals, so this is 353.94 meters. So what are we going to use here as a radius?
350.
Why did you round it down?
Because we want it less than 0.1 G, the F.
No.
Okay, if you round it down, let's go with your suggestion, and let's see
Oh, sorry,
how
it will go up the F.
Okay,
So we have
so
to make it
we round it up.
355.
Okay, actually I will go for 310, 360. Let's have an example from problem set 2. I'm gonna take this example, or okay, basically for surveying purposes, okay, we try not to we try to maintain values, okay, in you know uh, full numbers, it's an integer number. Why? For we have in surveying we define stations, so we need the stations to be integer numbers, so the surveyors life will be easier for them. So here the problem is, say, what is the length of the long chord for the horizontal curve shown in the sketch below? Okay, so basically what we are looking for is the long chord. That's the long chord. Let's do all the calculations that we need here. Let's go, that's the L of the curve, and let's see the tangent. So the tangent of this curve, how much, it equals, let's just draw this here. So these are R. This angle is delta. This angle is delta over 2. This is perpendicular. And this is perpendicular. Okay, so basically the tangent equals R tan delta over 2. So tangent equals 600 meters multiply tan, here it's 32 and 4 minutes and 50 seconds. So this is going to be 16 degrees, 2 minutes and 25 seconds. Can someone volunteer and do the calculation for us, please? The long chord this is perpendicular. So it's basically, this is R here, R sine,
Doctor,
yes,
equal 376.09.
376.09
609.
meters. Thank you. The long
Okay.
chord is basically 2R sine delta over 2. So here it's 2 multiply 600 multiply sine 16, I'm sorry, 16 to 25. So LC.
دكتور الأولى دكتور فيها غلط معلش.
Okay.
172.5.
Yeah.
This is 172.
15.
Okay. 172.5. Here.
$497.
Here the 197. Okay. 497.
Yeah.
No way.
0.36.
No way. It can't be if this number is correct, if this value is correct, this cannot be what you're saying. Let me just do the calculation myself. So I have 600 multiply.
I'm
Okay.
sorry, 331.5.
300.
Yeah.
331.58
58.
meters. Okay. Let's see L, the length of the curve, equal R multiply delta. So it's 600, but delta should be in radians, by the way. Multiply 32 degrees, 4 minutes, 50 seconds, divided by 180, multiply pi. So L equals, it should be greater than 331 and less than 345. In other words, L should be greater than LC and less than 2T, which makes sense because we have here 1T and another T here. So L should be less than twice this distance, but it should be greater than LC.
335.
So it equals 335 meters. This
0.95.
0.95.
Yeah.
Okay, hold a second. 0.95 meters. Okay, now if we are making a design for this curve, we are gonna use round this to be 360 meters. Why? Because we are gonna divide this curve into stations. Okay, so the surveyors, you are gonna put them in a terrible situation when you give them a length like this with fractions. It gives a chance for error and mistakes. Okay, so if you use L equals 360, they are gonna divide it into, if they are using stations every 20 meters, then they are gonna divide it into 18 stations and so on. Now you see why we round to whole numbers, and especially in tens. Any questions so far? Okay. So we move on now to the the transition from the normal cross section of the road to the super elevation. Okay, it's from tangent to curve transition. So there is a transition because we have, you know, there is the beginning of the curve, say here, that's straight line or tangent, and the curve starts here. So at this point on the curve, if we take a section here and take a section here, the cross section of the road looks like this. So that's section 1. Section 2, that's on the curve, we have a super elevation. So how can we make this transition from that symmetric shape to that banking shape, which is here? That's the normal crown, and that's the full super elevation on the curve side. So this is done on a gradually, and there is a transition, super elevation transition. The super elevation transition starts from the point of curvature or the beginning of the curve or at the end of the curve. So it's 2/3 before the end of the curve and 1/3 into the curve itself. Okay? And the length of this is the runoff length equal WN, that's the number, W, that's the width of traffic lane, that's the lane width, and N is number of lanes rotated, and I will explain what do you mean with rotated next. Delta, that's the maximum relative gradient percent. What do we mean with the maximum relative gradient percent? Basically, this slope, the rate of change, that's delta. Okay? PW, that's an adjustment factor for number of lanes rotated. That's an adjustment factor. And ED, that's the design super elevation. Because basically, the higher the super elevation, the longer L should be. Because we need to do make this transition as smooth as possible. So now let's see what we mean with N. Here, as you can see, we have one lane here and one lane here, and we are rotating around this point. So in this case, this line will this side will rotate, this lane will rotate here, then both will start rotating. So we have one lane rotating on both sides. So let me explain it to you better this way. If we have here one lane and one lane, and they are rotating about this pivot point. So the first rotation, they go to this point. Then usually we have 1.5% slope on the surface of the pavement. This is basically to drain water and rain and stuff like that. So once they get to both on the same 1.5%, okay, they start rotating around that pivot until they get to the slope that we need, which is E. That's the E design. Okay? Now, we can achieve that in a different way. For example, we can have our, okay, let me just draw this in a different color. We can have our road like this. Here we have one lane. We have one lane, and that's a pivot. Then the first, we have the initials or the standard slope for the surface, 1.5% here this way, and we have here 1.5%. Then this turns to be on the same line. So both sides, they have 1.5%. Okay, then in order to achieve our super elevation, we rotate around the edge. So here we have E, and here. In this case, how many lanes do we have rotating? 2. In the initial case here, the rotated around the pivot point in the center. We have only 1 lane rotation. So here N equal 1, here N equal 2, because we are rotating around the edge. And sometimes we do this, we rotate around the center, sometimes we rotate around the edge. And I will explain why. Okay? So I think we can do, for example, here N is 2, even if we are rotating around the center, because we have 2 lanes rotating. Here we have 3 lanes. Okay? And these are the adjustment factor for B. B adjustment factor, if we have N equal 1, so we have adjustment factor 1. We can rotate even, we don't have to rotate on the center, or we can rotate around this point in the middle of the lane. Okay? That depends on the topography and the situation that we have. So that's for the N and the BW that we have here. That's for the BW. The E design, that's given. The W, that's the lane width. We have the N, that's the number of lanes rotated. But what about D? Okay. The D, it depends, that's for delta. The delta, it depends on the design speed. Okay. So the maximum relative gradients, which is delta here. Okay. If we have the speed, design speed 20 kilometers per hour, we can go to 0.8%. That means the gradient of this is 0.8%. That means every 100 meters, we can go up 80 centimeters, or 0.8 meter. Okay. For a design speed of 90 kilometers per hour, this should be 0.47. For 120, should be 0.38. As you can see, the higher the speed, the lower the delta. Why? In order for the drivers to, feel a comfortable transition. Okay? Any questions so far? Okay. So the tangent run out, which that's at the end of the curve, because we have here. So if that was the curve, so we have here LR, and here we have L tangent. So here it's running up to make the, for the super elevation, and here it's, run out. Okay, so it's tangent run out. Okay, and the other one, it's called run off length. Okay. So basically, the length for the LT is 2/3 of LR. However, if we have a horizontal curve for a road that is, it has 2 directional, okay, usually the LT equal LR. Can someone explain to me why? I will explain to you why. Here we have LR for the vehicles approaching from this side. And if it's undivided rural highway, for example, then we have another traffic will be coming from this side. So we are going to have LR for this side and LR for those vehicles. So in both sides, we'll have LR on both sides. That's especially for undivided highway facility. Any questions? Okay. This is the configuration that shows that we have 1/3 of the LR is within the horizontal curve and 2/3 before the beginning of the point of the curvature. Okay, so that's point of curvature, this is point of tangent, this is point of intersection. Okay, so the point of intersection, that's the intersection between the two tangents initially. Now, the methods for attaining super elevation for undivided multi-lane highway. As I mentioned before, okay, that's the normal crown, that's section A here. Then we have a tangent run out. Initially, we come to slope 0. Then now we have the slope of 1.5%. Then here we start rotating gradually until we reach to the E percentage that we want to achieve. And as you can see, here we are rotating around the center line. The lanes are rotating around the center line. Okay. This is good, but there is an issue. Notice with me that's the inside of the curve. Okay, now the inside edge of the curve is significantly below its original state. So we have to bring the inside of the curve down this distance. Okay, so what's the problem with that? We will see it later. Now there is another strategy which rotating around the inside edge. So as you can see, the inside edge maintained the same elevation. So that's the elevation of the inside edge. Okay. Now rotating around the outside edge. Okay, and you see the inside edge went down significantly much higher. So as we can see, we have three strategies for attaining, okay, the super elevation: rotating around the inside edge, or rotating about the center, or rotating about the outside edge. What are the advantages and disadvantages of each strategy? Here, for example, if we have divided highway, we can rotate around the center for each direction. So what are the advantages here? Short, okay, because basically the number of lanes rotating, if this is a two lane, so it's one lane, we have a short transition. And we have minimum cut and fill, because we have to add fill here and we remove from here. So we're gonna so basically we are gonna remove this part and just build it here. And the same, we are gonna remove from here, but we are gonna build it here. But what are the disadvantages? I will show you now the disadvantages. Water drainage for the inner lanes. The inner lanes here, okay, had significantly, okay, went below this elevation. So if there is a rain or there is a problem with the drainage, we are going to have water accumulating this way. Okay, so that's one of the major problems for this strategy. Okay, so sometimes we go with this strategy. What is the advantage? It's good for water drainage. So if we are in a location that experiencing heavy rain and more frequent rains, okay, and the type of soil here cannot absorb water easily and there is poor drainage, then we go with this choice. The disadvantage from this strategy is that we need large amounts of filling material, because we have this material, this area, we need to add this fill. We're going to transport fill, and the problem not just in that. Basically, this will need a very careful compaction to make sure that it's not going to settle after we are, after construction. Okay, so that's because you have here, If we're saying, for example, that we have E equal maybe 5%, and we have this distance is 10 meters. So 10 meters multiply this 0.05. We have 10 multiplies 0.05 equals 0.5 meters. So we have 50 centimeters, okay, higher than the inner. So that's if assuming we have only 2 lanes. But if we have 3 lanes or maybe 15 meters, we have 75 centimeters. So it's not as simple as you might think. If we go to this strategy, which is basically turning around the edges, okay, so this is best in terms of safety. Good on cut and fill, because what you cut from here, we use it to fill here, so we don't have to transport. But it's average on water drainage for inner lanes. That means if there is drain, rain, we expect to have these lanes blocked, but these lanes are not blocked. So we have kind of half the problem solved, okay? So basically, the method we select for attaining the super elevation, it depends on the facility, on the location, on the criteria that we have. Any questions so far? Okay. I'm gonna stop here for 10 minutes break, and we will be back inshallah.
Inshallah.
Okay. Now we have discussed in the previous part of the lecture the design of the horizontal curve, especially the radius and super elevation. However, on horizontal curves, usually we do a lane widening. Why? Because there is usually an off-tracking for the vehicles traveling on horizontal curves. What is off-tracking? Off-tracking is basically a characteristic common to all vehicles, although much more pronounced with large design vehicles. Usually for trucks, you can feel it. For example, if that's a truck and it's turning, okay, so the truck basically, if it's driving straight, this is going to be the wheel tracks. But if it's turning, this is going to be its wheel track. And that depends on the radius, okay, and on the geometry of the design vehicle. Also, we have, different parts. We have here the off tracking for the front overhanging, so that's for the front overhanging of the front bumper, okay. And we have the wheel track, so the wheel track will be from here to this outer wheel track. So basically this vehicle will need this distance, okay, to make the turn without hitting other vehicles on the road. So the curve, the track width on curve U is calculated as follows. It's composed of U plus R minus R square minus L. Okay, so that's basically, that's the track width on the curve. So that's the wheel tracks. And U, that's the track width on tangent. So if that's the design vehicle, say for example, I'm sorry. If that's the U, okay, on, so these are the wheel tracks, the wheels here. That's a truck with, 3-axle truck. If it's going straight, that's gonna be U. If it's turning, it will need this width, U, capital U. That's what we have here. So calculating U will be according to this formula. The original track width plus R, that's the radius, minus R square minus summation of Li square. What are Li square? I'll tell you now. If we have, for example, an 18-wheeler, I'm sorry, it's something like that. That's 18-wheeler. So basically, there is a pivot. So that's L1. And from this pivot to these two axles, that's L2. So basically, this equation will be U, capital U, equal U small, that's the wheel track if it's going straight, plus R, that's the radius of the curve, minus summation R square minus L1 square plus L2 square. Clear? That's how we calculate the wheel track, the width of the wheel track on the curve. Okay? So that's one component. And here there is already curves for this, for the track width in meters, and that's the radius of the curve. And these are for different design vehicles. These are AAA. That's a passenger car. That's I think this is for buses. Okay, this is for trucks or buses also. It's for small trucks and buses. These are for trucks. Then we have the front overhang. The front overhang, basically, when a truck is turning, say for example, the truck is turning like this, and these are the front wheels. That's the front overhang. Because the front overhang exceeds the outer wheel track. So that's front overhang. So the front overhang is calculated this way. R square, that's the radius of the rotation of the curve. A multiplied A 2L minus plus A minus R. So what's A and what's L? A, that's the front overhang of the inner lane vehicle. Okay. L, that's the wheelbase of the single unit or tractor. So that means if we have a trailer like this, that's the front wheel. So basically A, this is A, okay, and this is L. Sometimes we have multiple components, so we can use the following equation. We have L2 here, okay, and we have here A2, so this is going to be A1, okay, and this is going to be A2, L2. So we calculate the highest, we take the highest for FA. The third component that's extra width allowance, that's for a matter of safety, which is 0.1 v over square root of r. So that's the design speed of the highway in kilometers per hour, and r is the radius in meters. So this part, or the z, this was introduced by the highway capacity manual or the highway capacity committee, and they selected it this way. And you know, so this is in kilometer per hour, this is in meters. Okay, any questions? So as we can see, there are several components that add to this. Okay, and as I mentioned, okay, so basically the curve widening, how much we need to increase the width of the curve. The curve widening, W, is WC minus WN. WC, that's the width of the traveled way on the curve. WN, that's the width of the traveled way on tangent. So that's the normal width, that's the width on the curve, and the difference between them, that's the extra winding that we need. So the width on the curve equal the following: N, number of lanes, plus U plus C, plus N minus 1, that's number of lanes, minus 1, multiply FA, that's a front overhang, plus Z. And as I mentioned before, Z, that's 0.1 V over square root of R. Okay, it's independent of design vehicle. But FA and U are dependent on the design vehicle. So what is C? Okay, so N, that's number of lanes. So what is C here? C basically the clearance. So for example, if we have, hold a second. If we have the truck driving this way, okay, and that's the width of the road, okay. Okay, let me just explain it to you in a layman term. If that's the lane, okay, and here we have the design vehicle. So it has U. It has this track width. So there is clearance on both sides. So we are going to assume that it's driving in the middle of the lane. So this will be C over 2, and here C over 2. Okay? So what is C over 2? That means C equal lane width minus the width of the design vehicle. Clear? So that's
Clear.
C. U, we calculated. N, these are the number of lanes. So why we have here N minus 1? N minus 1 because if we have number of lanes, for example, we will have overhang here, we have overhang here, but the outer lane, the overhang will not affect anybody. It's going to affect just the shoulder. Okay? That's why we subtract 1 here. Okay? Before we go further, we are going to just go and start solving examples. Any questions? So what is the problem here? We have the following. We have, for the given horizontal curve design, okay, it says that R, that's the radius, 200 meters, station of BI, that's the station of the point of intersection is this, and the I, that's the angle, the delta, is 36 and so on. And the given maximum super elevation 8%, 2-lane, 2-way, and no median. Lane width 3.6 meters, and level terrain, and 8% trucks, assume design trucks WB20. Determine the following: the safe speed for this curve. Okay, so let's start with this one. Let's first draw the problem. So we have a tangent here and a tangent here, and we have here delta equal. Let's just convert these ones into 11 divided by 60 plus 14 divided by 60. So this is 36 degrees point 236. So the curve, so that's the point of intersection, that's PI. That station equal 0, 2 plus 1, 4, 4, 6.5, 5. Oops. There is a problem apparently here. So this is 1. Oops. What's going on? 1, 4, 6.55. The curve starts from here and continue to here. So this is going to be point of curve, and that's point of tangent. And we have here R. So what is the safe speed for this curve? So V square over GR equal 0.01 E percent plus F lateral. So we need to find the safe speed. So V, that means we have V equal square root of G multiply R multiply 0.01 E percent plus F lateral. Let's substitute for the values that we know. So let's say V1 equal square root of 9.81 multiply, the radius is 200 multiply, okay, what is the super elevation? The maximum super elevation is 8%. Let's go with the 8%. So it's 0.08 plus, but we don't know what is the side friction. So it's plus FL. So let's assume, let V1 or V node equal 100 kilometers per hour. So if it's 100 kilometers per hour, that means let's go back to the curve for the horizontal, for the side friction. So here If we assume it's 100, that's initial, so we have 0.12. So FL 0.12. So let's substitute here. So we have square root of 200 multiply 9.81. That's 1965. Multiply 0.02, 0.08 plus 0.12. So this will be square root of, sorry, this is multiply 0.2 under the root. So this is 19. I'm sorry. Let me just. So this is going to be 19.809 meter per second, which is 71 kilometers per hour. So this will give us effect, side friction FL equal how much? 70. So that means 0.15. So let's give another iteration. V2 equal square root of 1960. I think it was 62, not 65. Multiply 0.08 plus 0.15 equal that's 21.24 multiply 3.6. This is going to be 76.47 kilometers per hour. That means somewhere here. So we have so that's the FL equal 0.145. Let's substitute here. V3 equal square root of 962 multiply 0.08 plus 0.145 equals square root of 1962 multiply 0.225. That's going to be 21.01 meter per second multiply 3.6. So we will have 75.6 kilometer per hour. As you can see now, the shift, it's converging. Okay, so we can say that safe speed equal 75 kilometers per hour, and we stop here. Okay, so we solved the problem using an iterative approach. Let's go to the second requirement, station of BC and
Sir.
PT. Excuse me?
دكتور
Yes.
على أي أساس اخترنا الانيشيال؟
Randomly.
يعني مثلا لو حطيناها 50 ما راح تطلع في الiteration.
No, if you put it 50, okay, it's gonna converge, it's gonna bounce to 70. Okay, let me just go with your suggestion, Yusuf. What you are saying, on what basis we selected 100. Let's go just let's go with 50. How much will be here? So here that's V1 equal square root of 1962 multiply
Okay.
0.08 plus 0.19, I think 0.195 or 0.19. So if we do that, 1962 multiply 0.27 under the root is going to be 23.016 meter per second. So this will be multiply 3.6. So that's 82.85 kilometers per hour. So FL will be how much? That's 80 here, okay? So it's going to be 0.14. So V2 equal 1962 multiply 0.22 under the root. So this is going to be 20.776 meter per second. So this will be, if we multiply it by 3.6, 74.79 kilometer per hour. FL, what for 74 is going to be 0.145. So back to what we have here. You see it now, Yusuf?
Yeah, دكتور.
Okay. Just believe me. Okay. Let's go
دكتور.
and no, never mind. Okay, I'm sorry. Just made a big mess here. Okay. Now we want to calculate the station for PC and PT. So we need to know the stations for this point and this point. In order to do that, we need to calculate the tangent length and the length of the curve. So the tangent of this curve will be tangent equal what? Equal R tan delta over 2. So it's 200 multiply tan, the angle is 36.236 divided by 2. So how much is this? 200 multiply 10.
65.44.
So this is 65.
0.44.
0.44 meters. Can you tell me the L would be how much? It's 120 something. It's going to be less than 130. Just from this. This multiplied by 2 equal 130.88 meters. So I'm expecting the length to be maybe 125, 122, something in that neighborhood. So let's check and see. So it's basically R multiply delta. So it's R, which is 200, multiply 36.236 divided by 180 multiply pi. How much, Yusuf? It's 126.
Yeah, 126.49.
0.49 meters. Okay, as long as it's less than half this, okay, we are in good shape. So let's, by the way, let's calculate the chord length. The chord length will be 2r sine delta over 2. So it's 2 multiply 200 multiply sine 36.23 over 2.
124.39.
124.39 meters. So you can see now the relationship between the chord length, the curve length, and double the tangent length. Okay? Now, let's calculate the station for the point of curvature. Equal basically the station for the point of intersection minus one tangent. So here the station of the point of intersection is 0, 2 plus 146.55 minus, how much was t? 65.44. So here we have 1 point, and here we have 1, and here we have 8, 0 plus 2, 0. So that's the station for the point of curvature. What about the station? If we add plus L, L is how much? 126.49. We get the station, so that's the station for the point of point of curvature. Now the station for the point of tangent is basically the station of the point. Okay, let me just remove this so you don't get confused. So this is the station for the point of curvature. Now the station for the point of tangent equal the station for the point of curvature plus length of the curve. Okay, so basically it's this point 0, 2 plus 081.11 plus the length of the curve, which is 126.49. So here we have 0, 6.702 plus 2, 0. So that's the station of the point of tangent. Okay. Now, the minimum horizontal side offset clearance for side distance. We didn't explain this yet. The lane widening in the curve. That's a good point. We need to calculate the lane widening on the curve. We have the design truck here is WB20. So let's get let me just get you the data for the WD20. Hold on for a second, please. Okay, unfortunately, I have only the W40 that's available for me, so we're going to use it for the time being, okay? So just let's just modify this. So we're going to just work with the WB40 for the time being. So let me just modify this WB40. So these are the specs that we have for the WB40. Now we want to calculate the curve widening. So first of all, we need to calculate the three components. We have U, and we have the front overhang, and we have the Z. So U equal the small u plus r minus square root of r square minus sigma li square. So in our case here, let's work through this part. What is u for this example? U is here. That's the normal wheel track width. So it's 2.44 plus r. R, that's the radius of design that we have, the radius of the curve, 200, minus square root of 200 square minus summation of L. Okay, how many L's do we have? We have one L here, and we have another L, which is here. We have a pivot point in the truck here, and another pivot point between the two axles here. So that's the 7. So here, this will be 3.81 square plus 7.77 square. So the width for this truck on that curve will be as following: 2.44 minus, I'm sorry, plus 200 minus square root of 200 square minus 3.81 square plus 7.77 square. So this will be 2.63 meters. See now the difference? It was on a straight line, the wheel track just occupying 2.44, 2 meters, 0.44. On a curve, it will occupy 2.63 meters. So there is an increase of almost 19 centimeters. Okay? So that's the first part. What about the front overhang? The front overhang equal, let me just review the formula for the front overhang. Okay, so that's the front overhang. The front overhang equals the square root of r square, which is 200 square, plus a multiply 2l plus a. So here we have the front value, this is a, and we have l, this is l. And we have another value here, okay, and this. So we are going to take these values. So here it's 0.91 multiply 2 multiply 3.81 plus 0.91. All of this under the square root. Then minus 200. So front overhang equals, actually we don't consider the back one here because it's called the front overhang, so it's going to be on this step. So here we have square root of 200 square plus 0.91 multiply 2 minus 3.81 plus 0.91, okay, minus 200. So here it's 0.0194, okay, meters. That means we're going to increase almost 2 centimeters just will be off the wheel track, okay. Of course, the 200-meter radius, you will not see this this pronounced width or dimensions. So what about the z? So now we are done with this. Z equal 0.1 v over square root of 200. So 0.1 z, that's 0.1 multiply, the speed is how much? 75 divided by square root for 200. So it's 0.1 times 75 divided by square root of 200. So we have 0.53 meters. So let's calculate now how much do we need for the widening. W small equal W curve minus W normal. So what's W normal? W normal, it's 2 multiply 3.6 equal 7.2 meters. W curve equal N multiply U, okay, plus C plus N minus 1 times front overhang plus Z. So what is C in our case? C equal lane width minus U, which is the normal wheel track. So the lane width is 3.6 minus 2.44. That means C, here we are trying to maintain the same clearance. Okay, so 3.6 minus 2.44, that's 1.16 meter. So the driver on the curve, is feeling the same clearance and maintaining the same clearance. He is not, there's no change in the clearance with other vehicles. So this is 2n, 2 multiply u is 2.63 plus 1.16 plus 2 minus 1 multiply 0.0194 plus z.53. So this will be plus 2.63 multiply 2 plus 1 multiply 0.0194 plus 0.53. So this will be 8.129 we take it as 8.1, let's make it 14 meters. So W equal 8.14 minus 7.2. So this will be 8.14 minus 7.2, 0.94 meters. So the travel way on the curve will increase by 94 centimeters. Okay. In other words, each lane will increase by 47 centimeters. So that means lane width on the curve will be 8.14 divided by 2 equal 4.07 meters. Any questions so far?
دكتور
Yes.
البوينت 91 الفرونت حق الفرونت اوفر هانج
Yes.
من وين جبناها البوينت 91
Here. Okay, let me just
شفت
okay, that's the 0.91. It's from the front bumper to the axle of the first wheel, of the front wheel. واضح؟ المسافة ما بين الصدام الأمامي للشاحنة، تمام، والأكس اللي بتلف حواليه اللي هي الفرونت أكسل للشاحنة للتراك. Okay?
اوكي
Okay. Any questions? That was a good question, by the way. Thank you. Any questions? Okay, guys, we're gonna stop here and wishing you a happy weekend and see you inshallah next week and see you next week inshallah.